Oh, hey, it's Dr. J. I'm here on the computer to show you how to graph a piecewise function using the graphing tools. If you've never done this before, it takes a little practice. So on the homework, you're going to first look at the what we call piece one, or what I call piece one. I'm just going to put P1. So that'll be x plus 6 when x is less than 2. And we'll make a little table of values. We only need to plot 2 points for each piece. Now remember, this is x is less than 2, so this will be an open hole at 2. I just put a little circle around the 2 to remind me it's an open hole. And then we go ahead and plug it in. So we'll plug in 2. 2 plus 6 will give us 8. And then let's plug in one more point. How about 0? 0 is a nice point. It's an easy intercept. Just do that mentally. 0 plus 6 is 6. So over here on our graphing tool, we'll take the half line, also known as a ray, and we'll start at 2, 8. And then we'll drag it down to 0, 6. Now, technically, there is an open hole right here, right? Because x is less than 2. However, I like to wait on the hole. Because it might get filled. And if it gets filled, you don't need to graph the hole. So coming back over to my graphing board, I now have to clear that out again because I didn't wait. So we have 2, 8 and 0, 6. So that's our ray or our half line. And at the moment, it is undetermined whether it's continuous or not. We'll get to that in a second. So now we'll go to piece 2. Piece 2 looks like an upside down parabola. We have negative x squared plus 4x plus 4. If I was needing more detail, I might, complete the square and rewrite this into a better form. But I just need a couple points. So x is greater than or equal to 2. And because it has the or equal to, this will be the solid dot or the point as opposed to an open hole. So we'll go ahead and plug in 2 here. X equals 2. We get negative. Negative stays outside the parentheses. 2 squared plus 4 times 2 plus 4. Which is negative 4 plus 8 plus 4, which is 8. And so because the hole is 2, 8, and the dot is also 2, 8, it's like a hole with a dot, I'm only going to plot the dot. So you will never see the actual hole. It'll get covered up with the dot. Now, in order to get the rest of the parabola, or the half parabola, I need at least one more point. So I could do anything greater than or equal to 2. So I could just do 3. I could do 4. I could do 5. I'm just going to do 3. There's no reason to go much farther than that. 3 squared plus 4 times 3 plus 4. If the parabola was a little more exotic or complicated or, had, fractions or decimals or something, I might need to be more careful about what I pick. But this is a pretty tame parabola here. So what do I get? 7? So 3 comma 7. So over here on my half parabola, I do have to start at the dot that I just plotted. So put another dot there. I know it seems redundant, but you'll see why when I'm done. And so that's going to be 2 comma 8 and then 3 comma 7. And submit. And it's green. Now I only got partial credit because I didn't finish the question, but I did get a green check on the graph, and then now I can determine the limits. So the limit as we approach 2 from the left looks like 8 as you approach it from the left. As we approach 2 from the right, it's also 8, which means the limit exists because these limits are equal to each other. So those are both 8, and that's the definition of continuity. So it is continuous at the point, and I get full credit, which is always nice. Let me scroll down and make sure you can see all the answers. Not too bad, huh? So let's go ahead and do number 5 then. And I'm basically just doing your homework for you, but we're going to see more of these in the future, and then you can just follow this technique when we're graphing these types of functions. So piecewise functions can be tricky. I know I've spent several hours getting them just right. So we'll call this one, well, it's still called f of x, but let's again look at the piece 1. This time piece 1 is the parabola. It is written in a slightly different form. It's written in vertex form. And this time x is less than -2. Oh, it's actually less than or equal to -2. So that one's going to be the solid dot, right? The or equal to tells you that it's going to be a dot. I do get one free point. I get the vertex, -2, -2. That'll be the vertex. Let me show you how that works. I'm plugging in -2. It's going to be a solid dot, not a hole. So put like maybe a little dot symbol right here to remind me. And then suppose you don't know that the y value is -2. You can actually tell by this. This is the y value of the vertex. You should probably remember this from algebra. When you plug in the opposite of this coordinate, that's the x value of the vertex. So the x value of the vertex is the opposite of 2, which is -2. This becomes 0. And that always happens. So whenever you have a parabola or quadratic function that's in this vertex form, the inside of the parentheses, when you plug in the opposite of this value, so we sometimes call this value h, and so this is -h, it always zeroes out. The inside of the parentheses becomes 0, and it just gives you the y value, which in this case is also -2. I don't know how much more helpful that is than just having it in the other form, which is the expanded, or also known as standard form, in which there's no parentheses. It's really a matter of opinion, a matter of taste. So there's my P1. I do need a second dot. So remember, x is less than or equal to -2. So I can't do -1. Instead, I'm going to do -3. Or I could also do -4, -5, something less than or equal to -2. So again, I'm plugging it in here for x. So -3 plus 2 squared minus 2 is -1 squared minus 2 is -1. So there's my half parabola. Now in the tool, it looks like an upside down and it looks like the right half, but this one's actually going to be right side up. And it's going to be the left half. So just choose the appropriate tool. All right. Now I do have a solid dot at -2. All right. So I'm going to go ahead and put that. You don't have to wait on dots. You should wait on the hole though, because if the hole ends up right on top of the dot, then you don't have to draw it. Let's go ahead and wait on that. Remember, the hole comes from the side of the parabola that's open. So that'll be piece 2, 1/2 x minus 2. And this is for x greater than -2. So this will be the open hole. So I start with -2, plug it in, 1/2 times -2 minus 2 is -1 minus 2, which is -3. All right. So now ask ourselves, does the hole match the dot? The dot was -2, -2. The hole is -2, -3. It's not a match. They do not match. So that means when I go to graph it, you're going to see the hole is at -2, -3 right there. All right. And then now I need to get the rest of the line. So the rest of the line is 1/2 x minus 2. I always just go with 0 when you're graphing a line. You get an automatic free point. If you plug in 0 for x, it's just going to kill the 1/2 and you'll get 0 minus 2, which will be -2. So again, I got to start my line at the hole and then go to -2 on the y-axis and submit. Good. All right, I'm always happy when that happens, especially when there's multiple pieces, because all it takes is one piece to be offline there. So now we can answer the limits. We got the limit as x approaches -2 from the left is -2. That's the dot. As we approach it from the right, it's -3. That's the hole. Because the hole and the dot do not match up, it does not exist. And therefore, the function is not continuous at that point. Okay. I wouldn't say there's a lot of this computer graphing in this course. There was a heck of a lot more of it in an algebra course. But in calculus, in order to sort of describe the nature of a function, in particular limits in this chapter, it becomes necessary to just do a few graphs. If you have any other issues with graphing, let me know as soon as possible, and I'll try to cover those. This particular one, I'm the one that had the trouble with it. It took me a while to finally get it to mark it right. And I thought to myself, well, if I had to do it 10 times to get it to mark it, green, I should probably go over it and show you guys how to get it right. Maybe on your first try. Maybe, you won't have to suffer like I did. All right. And then in my last video, which was the end of the chapter, I did not get a chance to go over this type of question. I know I did 10 or 12 examples, but I don't think I did this particular one. So I'm going to talk a little bit about this, and I'm doing this on my computer. I don't have my whole studio with my whiteboard set up today, so this will be I don't know, is this high tech? So it's a little bit too techy for me, but I think we can make it work. A lot less cameras involved. This is just me writing on my computer screen here. All right, so we have the piecewise function 5 to the x plus 7, where x is less than 0. So this question doesn't directly ask you to take limits, right? But I mean, the chapter is called limits. So let's go ahead and take the limit as x approaches 0 from the left of f of x, right? Because we're interested in the continuity at the cutoff values. And this function has 2 cutoff values. We have 0 and 4. So we're just going to take them one at a time. So that's going to be 5 to the 0 plus 7, which is equal to 1 plus 7, which is equal to 8. So that's the limit as x approaches 0 from the left. Well, if we want to see if it's continuous, we have to also take the limit as x approaches 0 from the right. And that'll be the second piece. X looks like greater than or equal to 0. So we'll use the second piece. We have 8 minus 3/4 times 0, which is clearly 8 minus 0, which is 8. That's pretty good. These agree with each other. And so that means the limit exists, and the limit is, in fact, 8. All right. Also, is f of 0 defined? Yes, it is. It says x is greater than or equal to 0, less than 4. Anytime you see or equal to, right, that means the same thing as x is equal to 0, right? Or x is greater than 0. That's what greater than or equal to means, right? It means or greater than or equal to. It's like soup or salad. It's one or the other. So the or equal to is defined. It's a valid point on the graph. Yes. So yes. I almost wrote yef. Yes. F of 0 is just 8. It's this value right here. So this limit not only represents the limit of the function, but it represents the value of the function at that point. So that means f is continuous, let's say cont at 0. So that's the first critical value, 0. I'm going to answer both the questions simultaneously. First, I want to figure out the continuity first. So I know it's continuous at 0. Now, what about 4? All right, so the limit as x approaches 4 from the left. So the left side of 4 is the middle piece. So it says x is less than 4. So that's going to be 8 minus 3/4 times 4, which is 8 minus 3, which is 5. See, the 4s will cancel out. Or you could, I like to actually do it the long way. 3 times 4 is 12. 12 divided by 4 is 3. Canceling is okay. There's nothing wrong with it if you get the right answer, but I always like to verify that I'm not just crossing stuff off that actually is not valid. So that is definitely a valid canceling. So as x approaches 4 from the right, now I'm in the third piece. Now, I do have to be careful with square roots. I'm plugging in numbers that are greater than 4, greater than or equal to 4. In this case, because it's the limit, I'm actually plugging in 4. And I got to make sure that it's defined at 4. And it is, but you should just make sure that you're not causing, a restricted value such as an imaginary or division by 0 or something like that. So that would be the square root of 16 minus 28 plus 12, which is the square root of oh God, what is that? 0. Yeah, let's double check that. 16 minus 28 is negative 12. Negative 12 plus 12, check, that's equal to 0. That's a pretty close call there. Square root of 0 is 0. So these do not agree with each other. Yeah, they do not agree with each other. So the limit does not exist. So f is not continuous at x equals 4. All right. So now when I go to my function here, the largest possible interval, well, it says x is less than 0. So negative infinity, that's less than 0. All right. Now, it's continuous all the way to 4. Right? Because we already determined the function was continuous at 0. This is asking where is it continuous? So we're going right past 0. 0 is in there, right? We don't want to mention it because the problem with mentioning it, if you put a 0, that means that it's not continuous at 0. But it is, so there it is. 0 is in that interval right there. But then at 4, it becomes discontinuous. And then we're going to do the union. Where's my union symbol? I'll just do a U here. My computer's about to die. All right, that's weird we don't get a union symbol. Oh, there it is. Yeah, let's use the fancy one. Union symbol. If you don't see the union symbol, you can just do the capital letter U. All right, and then it's discontinuous at 4. So notice the open parentheses at 4. Now here's the trouble. Where do I stop? Yeah, do I go all the way to infinity? Do I go all the way to infinity? I do. Yeah, it's hard to tell, but this is a radical function, square root. It's a square root function of a polynomial. All right. And the square root function goes off to infinity. Yeah. And so you're taking, I could take the limit if I really wanted to, but just trust me, it goes to infinity. If you take the limit as x goes to infinity, well, like we did in a previous lecture, if you plugged in a very large number for x, you would see that goes to infinity. All right. Now, when a function is not piecewise, then the answer to the first part and the second part are typically the same for most functions, right? We had that whole list of functions there. But in this case, the domain and the continuity are different, right? Because 4 is actually in the domain includes the 4. So basically we're saying 4 is part of the function, right? It's not excluded from the function, from the domain of the function. It's only excluded from the continuity intervals. And you'll see that that's right. And then the last couple questions here, I'm going to do in just a second. I'm trying not to do all of them. I want you to do some of them, but my goal is to show you sort of one of each type. So if you want to look at what we just did, the graph of number 12, kind of just summarize everything here. We have a point at 0, 8. Hold on, let me scroll back so you can see what I'm talking about. I'm talking about the one we just got right. All right. And I'm not going to do a super detailed graph here. I just want to kind of fake it here. So this is how you do a quick graph. You know, you got 0, 8. All right. Now, technically, it's a hole at first. And then when x is less than 0, that's on the left-hand side, going all the way to negative infinity. It looks like an exponential function like this. And although you can't really see it, it has this horizontal asymptote at 7. This one would be very difficult to do with a computer. So you see that plus 7 is how high the asymptote is. All right, so it is going towards negative infinity, but it's never going to go below 7. And then right at 8, the hole gets filled in. And then you go all the way to 4, 0. And then you have this point here, 4, 5. Should blow that up a little bit. And you have a straight line going from a solid dot to an open hole. Now, these limits do not exist, or this limit does not exist. And this is what I meant when I said on the left side, you get a 5 for the limit. So it's 4, 5. That's a hole. On the right side, you get 4, 0, which is a dot. And then this graph kind of looks like this. So this is for x greater than or equal to 4. So that's what the graph of number 12 looks like. So again, I like to summarize. The domain goes from negative infinity all the way to positive infinity. But the continuity goes from negative infinity to 4, and then because there's a break at 4, it stops being continuous, and then it's continuous from 4 to infinity. Interesting, and this is, I'm not changing any of my previous answers or changing any of the assignments, but I should just make sort of a quality control comment here. One could argue, based on the graph, they would lose the argument, but you might think, well, because this is a solid dot at 4, shouldn't we have a bracket at 4, right? Like, I mean, it is a square root graph. In some of the previous questions when we had square roots, I would put a bracket, right? Now, that's true. The bracket is true for the domain, right? So 4 is part of the domain. So you can think of it like on one side, it's a square bracket. That's the solid dot. And on the other side, it's an open parenthesis, and the two things come together. That's true for the domain. But for continuity, it's never a bracket. All right. When I say continuous, a continuous interval, an interval of which a graph is continuous, is always an open interval. All right. And it goes back to the definition of the limit. Right? In order to be continuous, the limit has to exist. And if you have a solid dot on one side and then nothing on the other side, or perhaps an asymptote or a hole or something else, then that limit doesn't exist. And so it's always an open parenthesis. All right. So if I'm just asking for domain, there's been some previous examples where you can use the square bracket for domain. If it's, greater than or equal to. Got to have that or equal to. But if I'm asking for a continuity interval on which it's continuous, it's always an open interval. All right, let's go ahead and do another one. So let's just do this last one. I guess let's see, do we have time for both of these? Let's just do the last one. I think you can figure out number 14. I'll show you how to do 50 and you can figure out 14. Number 15, we have this function here. So what we want to do is we want to take the limit. So we're trying to find k, right? This is the very end of the concept on continuity. It's what we call a removable discontinuity, which really means to patch the hole. Right? You are removing the discontinuity by replacing the hole with a dot, and the dot has to go in just the right spot to patch the hole. So go towards the critical value. It should always be pretty obvious what the critical value is. In number 15, it's -4. And we'll do from the left, and then we'll do it from the right. So on the left, we're going -4 squared minus 16 over -4 plus 4. And you get 0 over 0, which means you can't do it. So you have to use some algebra. X squared minus 16 over x plus 4. Remember the algebraic techniques. That's x minus 4, x plus 4. I guess I should have seen this coming. But I wanted to show you that that's may never go away. The 0 over 0 thing tells you can't plug in the number yet. You got to first cancel, simplify and cancel. And now you can plug in the -4 for x. So the limit on the left is -8. All right. So remember, because this says x is less than -4, this is a hole at -4, -8. All right. Now we want to look at the dot. So the dot is for the right side. The limit as x goes to -4 from the right. So we've got this crazy looking function, but it's actually crazier than it looks crazier than it actually is. We have a k, which we don't know. K is an unknown value. We have an x squared, but we do know what x squared is. It's -4 squared. And then we have the ln of 5 plus -4. So all this means is 16k, -4 squared, 16, then times k, minus the ln of 1. Now, ln is the natural log. So you don't actually think, you think e, right? A natural logarithm is a logarithm base e. That's why e is called the natural base. So when I say natural log of 1, what I'm really saying is e to some power is 1, right? And I already filled in the power. The power is going to be 0. So this becomes 16k minus 0. That's your crash course in logarithms. That would have been true for any logarithm. It doesn't matter that it was e. It does matter that the base becomes e, but the result of the problem would have been the same no matter what the log is. So I sometimes throw out different types of logarithms to keep your algebra skills in check. But remember, they're all treated exactly the same way. They just have different bases, but the technique is the same. All right, and so now we have 16k. Now remember, this is the dot because x is greater than or equal to -4. So the dot has the or equal to. It's kind of like the combination of two lines, right? In some of the questions, I actually have one line will say equal to and another line will say greater than. Look right above it, number 14. In number 14, there's two separate lines for that. This is like just combining those two lines into one equation. And our goal is for the limit on the left to be equal to the limit on the right. So we're just going to set them equal to each other. And solve for k. So divide by 16, divide by positive 16. Dividing by positive 16. And 8, -8 divided by 16 is -1/2. And that should do it, folks. Okay, well, I hope that was helpful. From time to time, if you have any individual questions, email me or come see me on Zoom. This is how I often do my Zoom hours. It's not this messy, but I'll bring up my electronic whiteboard, or I'll bring up the homework and we can go over some questions. Or you can send me requests and I'll make short videos like this. I know this wasn't very short. I think that was 30 some minutes, but it was necessary because now we're done with the chapter. So until we see each other again, I'm Dr. Jordan, and I'll see you on the internet.